In this video, I'd like to work through a few application problems of our derivatives. We've been speaking of computing derivatives for a few weeks now, and now I'd like to at least address a few opportunities where we can use derivatives in a real-world setting. Carbon-14 is a radioactive isotope, and it's used to date objects. A0, we call this A0 or A sub 0, represents the initial amount of carbon-14 in an object, and the quantity of carbon-14 that remains after T number of years is given to us in this equation. Part A, a tree originally containing 185 micrograms of carbon-14 is now 500 years old. At what rate is the carbon-14 decaying? So when I read this problem, I see the question, at what rate is the carbon-14 decaying? And rate to me just jumps out on the page, and this screams derivative. When we see the phrase rate, we are talking about derivatives. So I'm going to enter some values into the equation and then compute the derivative. Now I know that the problem does say that we're curious how much of the carbon-14, or I'm sorry, not how much of the carbon-14, but at what rate the carbon-14 is decaying after 500 years. But the formula right now, I'm not going to input that value. We'll use that inside the derivative. Let's go ahead and compute the derivative now. I've got 185 that's acting as a constant, and I've got this other function, e to the kt power. So I'm going to use the formula from our formula rules to compute that derivative. That rule states that this k value, this multiplier times our independent variable, comes down to the front. So we'll write negative 0.000121 times e to that same power, negative 0.000121 times t. Now we can clean this up a little bit, so I will go ahead and multiply. And we have a prime of t at negative 0.022385 e to this power. Now this function is the original function's derivative. While the original function tells us the amount of the carbon-14 at any given time, this new function down here tells us the rate at which the amount of carbon is changing. And that's exactly what this problem is after. What is the rate at which the carbon is decaying after 500 years? So we will evaluate this derivative at the value, t value, of 500. And my calculator off screen tells me that the result here is negative 0.021071. I'm rounding. This implies a negative 2.1071%. It's decaying at a rate of 2% per year after 500 years. While I'm not real familiar with carbon dating, I would assume that the rate of decay changes at different times. So the decay rate might be much more quick at the beginning of the time period, and it might be slowing as the years progress. What we know at this point is that after 500 years, the carbon is decaying at a rate of 2% per year. In this economics example, we've got a couple phrases here. The cost of producing a certain quantity of a product is given. So this capital C represents total cost, and that's what's being referenced down here. Find the cost and the marginal cost. Well, marginal cost, this phrase is the phrase that we use to describe the cost per unit, or the cost at margins. This one here is a rate. And so again, if we're dealing with rates, then that phrase should scream derivative to you, and we will need to compute the derivative. But first, finding the cost when Q is equal to 50. What's the total cost to produce 50 of these items? We would simply use the function and calculate C at 50. And here's the setup and the result off the calculator. $1,365.47. So whatever these products are, if I try to produce 50 of them, the cost would be $1,365.45. So the next thing that we'll need to do is compute the derivative of cost. This is the function that will establish our marginal cost. Now you should recognize that the cost function has the sum of two separate functions, so we can find the derivative of each separately. The derivative of this first function is nice because it's just a constant here. We know that that derivative is 0. So now we'll just focus on the remaining function to compute its derivative. The remaining function has a constant next to an e to the kt exponent, or e to the kx exponent. And the derivative here, much like the last example, 0.05 times e to the 0.05 q power. And simplified just a little bit more, 1.5 e to the 0.05 q. And this formula represents the marginal cost at any given time. Now again, the marginal cost describes the rate, or how much it costs to produce each unit. And what you need to realize is that in businesses, the rate to produce each unit differs with the number of units that you actually produce. If I'm only building one table and chair set in my wood shop, that would cost a lot of money to outfit the shop and pay for the electricity and the supplies to build just one set. But if I were to make 150 sets, then the cost per unit would then decrease. And so that's the notion that we're trying to describe here. This question would like to know what is the cost per unit when we produce 50 units, and we can substitute an appropriate Q value to interpret that result. Here's the setup and the result off the calculator, $18.27. So whatever the object is that's being created in this problem, if we make 50 of them, the cost per unit is $18.27. Now I do actually need to backtrack a little bit. The cost per unit is not $18.27, but the additional cost to produce one more unit is $18.27. The actual cost per unit would have been the total cost divided by 50, but the additional cost, if we're in the middle of a production run, if we wanted to produce one more of these items, the next item would cost $18.27. This value could be used to determine whether or not the production should continue and whether it would be worthwhile for us to manufacture one more item. Okay, and in this third example, if you invest P dollars, some identified value, in a bank account, with an interest rate of R%, then after T years you will have B dollars in the account following this equation. Our objective in part A is to find the derivative of B with respect to T, assuming that P and R are constant. Now, we don't know what the value for P and R is, but we do know is that these are supposed to represent some number, some constant value. They're not changing. So when computing our derivative, the only variable is the letter T, and the independent variable is letter T, and the dependent variable is letter B. So those are the only two values that will change in this equation. With that known, we can compute the derivative of B with respect to T. In essence, we have some constant value times a base raised to a power. And we have a rule that helps us identify the derivative of some base to an exponent power. We'll utilize that here in part A. So again, if B is equal to this equation, then D b dt, the derivative of b with respect to t, would be the derivative with respect to t of this entire equation. And when calculating the derivative of a function with a constant in front, we can move that constant to the outside. And here again, even though this looks rather complicated on the interior of this function, we're really just being asked to find the derivative of some base raised to an exponent t. I'm using this rule because the base does not change. R is a constant value. 1 plus r over 100 does not change. It acts just like a number. So since the derivative of a base to power is equal to that base raised to a power times the natural log of b, then the derivative in this case should look something like this. Now this seems very complicated at first, but if we were to substitute numbers in place of p and r, then the expression itself here will simplify to a single numerical value. Let me show you what I mean. If I had invested $1,000 in some account that returned an interest of 3% per year, and I left that alone for 5 years, the account would increase in value to $1,159.27. That's what B would be equal to after 5 years. What we've expressed down here is an expression that helps us determine the value dB dt. And if I make the substitution here, these are the same values from the expression before, $1,000 invested at 3% interest for 5 years. This calculated result returns 34.27. Now, since we're dealing with a rate here, this is the derivative of our balance. This is telling us that our balance is changing $34.27 per year. It's increasing by approximately $34.27 per year after left alone for 5 years' time. dB dt is the rate of change of our balance with respect to time. How does our ending balance change with respect to time? I hope you find this video helpful in computing derivatives and understanding the application of each. I think I'll spend a few moments at the end of this video. I'll turn the microphone off and work through a few of the implicit differentiation problems. So these are the practice problems for implicit derivatives that I handed out on Monday. I'll select a few and work through them silently on the screen so that you can watch my technique.